Fantastic. Thank you again. Good afternoon, everyone. So today I just saw a little late in the game that I was supposed to talk about machine learning. So what instead probably I'm going to do is to sort of using a case study of one line of work we do in our laboratory, particularly with colleagues like I know Jim gave a talk on vision. He's a close collaborator of mine, and Donna's here. Um, show some illustrative aspects of both signal processing and machine learning. So my lab does what I call signal analysis and interpretation. We are in a time where it's amazing confluence of both sensing, the amount of data one could gather from all kinds of things about people, with the environment, and so on. It's amazing. In addition to the ability to compute and also communicate the data across places, so that's opened up lots of possibilities for us. So one of the big things, as a part of this, D to K, right? So data to knowledge, right? One needs to actually be able to sort of analyze the signal. By that, what we mean, acquire the right signal. Maybe make sure it's conducive to the kinds of analytics and statistical processing one wants to do. Transform it in different forms. Usually these are multimodal, different forms. You want to reconcile them. And then also sort of begin to interpret it, basically mapping it to constructs that will help, either better scientific understanding or help us with decision making, or even autonomy. Trying to make drive some interventions that are based on, hey, this crosses this threshold, I'm going to do this particular thing. So this is a kind of business that we are engaged in. So particularly in this behavioral signal processing, what our aspiration is to see how we can seek a window into this human mind and human state through sort of engineering techniques, particularly signal processing and machine learning. It's a lot of the things about constructs like affective state. They're hidden from direct observations. You only have some signals that you can use to sort of do the system identification, if you may, and track. So how are we going to do this? It's a very mathematically interesting problem. So just as a sort of sort of learning goals, by behavioral signal processing, there's two things the way I think about it. One, it helps us do things we know well to do. Experts in say major depressive disorder, they know the kind of constructs they're after. Perhaps this will provide a suite of techniques to do or measure things more efficiently, more consistently, and map data to constructs to help decision making. But also the equally exciting is this whole creating tools for discovery. Basically, I think Dave just mentioned, you have to collect the right amount of data, because not too much data is not necessarily useful, or too little data. But the thing is, like, if we can create sort of novel data with the appropriate analytic sort of approaches, one could even gain insights we haven't imagined, that we haven't planned, in our hypothesis. That's also exciting part, and so signal processing enables. So I think Donna gave a talk to open up. She sort of positioned the importance of behavioral sort of analysis. It's across domains. Whether it is in social science scholarship to user modeling. When we go online, they're modeling our behavior. Where did you click? Where did you look? And then where will you potentially click? And so I can show you the right ads. It's all statistical modeling and machine learning. To in education, to actually health and well-being, sort of behavior analysis is very central. So the role of engineering is like we can ask, hey, what's got engineering got to do with this domain? So I have lots of examples, but I chose two examples, two domains I work on. One is the study of couples who are in distress in their relationships, marital therapy. So researchers, one of my colleagues is Andy Christensen from UCLA. In fact, they've been doing this. They look for things like, how do we characterize affective dynamics? How do you characterize humor and blame patterns? These are varying degrees of abstraction, but nevertheless, how do they do this mapping? They observe, for example, couples like this.
And I want you to just come home at a more reasonable time, rather than walking in the door at 11.
See, I just don't think you understand how much I have to do, like what my work entails.
Well, what is there to understand?
And so on, right? So what do they do? So they have coding systems that they create for this domain, and then they try to have, hopefully, usually psychology undergrads, to sit and map these to the scale of 1 to 9, how much humor was there, and so on. So, but if you think about it in terms of signals, right, they're looking at both explicitly conveyed signals like verbal signals, language use, the intonation of the voice, to all these latent nonverbal cues, right? You saw the approach avoidance behavior, this guy, turning around and all. So you can imagine translating these kinds of sort of cues into signals and being able to measure that and to map them. You can start formulating that. So analyze it and then learn these patterns basically using machine learning into constructs. So that's the example, sort of one kind of example I want to sort of illustrate. The second domain is also very dear to me. It's like autism spectrum disorder. The prevalence rating keeps dropping down. We have no idea. It's 1 in 68 right now in this country. So there are a number of things needs there, including both sort of making more quantitative some of these diagnostic criteria, but also the ability to track behavior change and so on. In fact, this is one of the things that inspired Jim, who led this expedition. So he's leading this expeditions with a whole bunch of characters, including me, to inspire us to do this. So here, some of the computational targets could be, modeling joint attention, modeling turn-taking behavior, computing things like shared enjoyment gets a little more abstract, but also, more things that can't be coded by human observers, like, behavioral synchrony. So, for example, one of the things that we've learned that what you see is not what necessarily you get, because some of the expressed aspects of behavior, like social anxiety, may not be visible using the typical cues that one would expect. Like, for example, you might need to have access to physiological sort of cues. So how do you then reconcile observable sort of visual cues with these kinds of things? So let me play this video.
And then he got stung like these to be a lion again, to be a regular lion again.
Yeah, good job.
So it's very complex, right? Just two, a parent and a child making a story together. And here you saw sort of the speech signal, the intonation patterns, and you saw this pops, who's talking when, so turn-taking information. But also this is, for example, the electrodermal activity of the child and the parent. And you saw when they are sort of aligning and going out, sort of some measure of arousal and synchrony in that. So immediately you can start thinking about, how do I sort of get all these different pieces of information? Each of it comes at different rates, bears different information, complementary, sort of some of them are sort of independent of one another. Then you want to map it to constructs like things like, okay, how do I compute or even predict things like, response to a contingent situation, so on. So you can see the kinds of possibilities engineering can play in these kind of behavioral analysis domains. So these two examples. So in general, multimodal behavioral signals provide a window into these internal state and processes. Some are overtly sort of available to us and directly observable, like vocal expressions, facial expressions, body posture. Others are not, like electrodermal response or neural measures. But being able to sort of try to get a handle on them is important for us to understand how humans encode information, these various signals. I'll delve a little deeper into that, and also be a process, because many times human interaction involves us being sort of transmitter of information and receiver of information, and this happens in a very complex dance that we all do. And so in that sense, people's judgment of others' behavior is as equally important. Again, using the autism domain is one of the big things that comes as a barrier to social interaction is the perception of cues that people, vocal cues or facial expressions often are perceived as, described as awkward or unnatural. So it comes as a barrier for people to interact or sustain interaction. So measuring and quantifying these kinds of, nuanced and, constructs is fairly challenging for engineers. It's no longer, okay, identify an object or even, recognize speech. It's much more than that. So, but behavioral signal processing, basically, we're very interested in quantifying both express behavior and also the felt sense to mainly facilitate sort of human analysis and decision making. And the outcome I call sort of a behavioral informatics. And as a part of it, we can also have some autonomy. We can make a virtual human or a robot do things, but that's a small part of it. I think analyzing and interpreting signals is very important. And think about it, lots of advances are happening. You heard, I didn't listen to Jim talk about some advances in computer vision. A lot of things are happening in audio processing. These days, Siri works pretty well. Or Google Voice, if you think about it, and physiological signal processing. So these are sort of key enablers to take these mid-level, raw signals to mid-level representations. But what is important is sort of, we have to think about this as sort of a pipeline that involves sort of, acquiring rich and ecologically valid data, because, when you do measurements, you want to make sure it's, we are doing the right thing, not disturbing other things, but also, have the flexibility of making measurements where we want, right? Much of ML talks about, sort of breaking this barrier off, where you do want to do the measurements, and you want to do measurements where it is happening and interesting. And doing it in the right way as a part of signal processing is important, because we don't need to make the problem more difficult than it is. For video, there are certain good principles of how you acquire data. Audio also, what kind of microphone is possible. Same with certain physiological sensor. Do we need to put the right appropriate gel or so on, and it's often has constraints about is that possible? For example, kids with autism have sensory sort of issues, so we can probably, ideally it would be nice to put a band maybe for this kid, can't do it. So constantly signal processing worries about how do you do engineering trade-offs between the quality of data that we can acquire and what we can do with it. So there's no perfect solution, but one needs to think about these engineering questions in mind. The next big building block is the analysis. Once you have the data of various forms, we can answer a lot of different things with these low-level cues. Who does this data belong to? So biometrics question. What does it convey? The semantics of it, like when did it happen? The timing information. How was it generated? Location information, and so on. And then with that, we can actually sort of get closer to the domain of interest. Every domain, right? We study, for example, psychotherapy and addiction. They have good ways of thinking about what both the outcome from a client perspective and response, but also efficacy measure of the psychotherapy. So they have a language. If you go to a different domain, they have a different language of describing the outcomes. So we want to see how we can take these measurements, these signals, and map it to these kinds of contexts. And that's where machine learning comes in pretty handy. Basically, machine learning, it's nothing but statistics. Builds on the foundation of good statistics, estimation, information theory, with computational sort of algorithms and advances to make things really apply on data. Be able to worry about complexity, and are we able to do this rapidly, efficiently on devices in the cloud and all that stuff. So it's nothing but, and basically trying to figure out patterns in data where we sort of know about patterns we are looking for, and sometimes we don't know. So it has all these kinds of dealing with uncertainty and observation, subjectivity and descriptions, and so on. So one point I also want to sort of emphasize is this sort of it's these kinds of machine techniques are not sort of in isolation. At some point, they're going to inform some decision making by an expert. This clinician has to make a diagnostic decision or figure out what intervention is appropriate. There could be autonomy in cases, but in many cases, the decision making comes in. So, in fact, these machine learning often learns from what humans are looking for. So, whether in terms of, hey, these are the cues, vocal cues, intonational cues. For example, let's again take autism, right? If you look at the ADOS, which is Autism Diagnostic Observation Schedule, the one of the diagnostic instruments, it's got multiple elements. One of them is atypical prosody, right? It says, looks for, and it has a very qualitative description saying, okay, sort of atypical rhythm, either low volume or high volume. And it's very qualitative, and the trained clinician is able to map it to number 1, 2, 3, right? This is what happens. Now, you can ask them what are the cues they are looking for from the description. Then you can build signal processing to figure out, okay, I need to figure out intonational cues, I need to figure out timing cues from the signal. And then we can see what people do, learn from those input-output maps, and let the algorithm learn what the humans were trying to do. So we can have this as in a closed loop. So human-in-the-loop-based sort of algorithmic development is a very exciting area. And together, I think, they can help with things like everything from screening to sort of intervention planning. So in summary, behavioral signal processing sort of is computing of or by sort of humans. I strongly believe in that part, and to support rather than supplant sort of human decision making, particularly in the health domain, right? There's lots of different kinds of expertise that come together, and it's very hard to say, well, some computational tool will sort of replace this. It's actually, in support of many activities, and so the next few slides, I'm going to use speech processing as one sort of behavioral signals, the human speech, and show some of these examples of signal processing in machine learning. So speech is very an interesting signal, right? It's created by humans for humans, right? And so much variability across speakers, age, gender, socioeconomic levels, and cognitive abilities. Two, depending on the nature of interaction, whether you're in a dyadic interaction or a small group interaction or just lecturing like me right now. Two, where these things happen. Is it happening in, as they're walking around in a crowded street, or is it in a quiet room? Two, what kind of data capture did you have? And the processing goals and purpose, or what are we trying to use this for? Do we want to know how much social interaction this person had, when they were in proximity to people? How much did they talk to them, right? This might be sort of a marker for sort of tracking, people with depressive disorders, right? How do you do that? So it's a very complex thing, the speech processing. So people have done a lot of different things to derive both linguistic and paralinguistic information from just a simple audio signal, right? And so various levels of representations hence have been derived. Everything from words, which tell you something, to actually aspects of speech rate, tells you something about there's the cognitive load, that tells something about their affective state, and so on. And so as a result, there's a whole range of enabling technologies there. It's not one technology. So everything from figuring out in a stream of audio where there is human speech, right? It's a very interesting problem still, it's a very actively researched problem, very simplistic, but, Department of Defense, I think, Santosh mentioned, still interested in, because audio is could be so variable, how do you detect voice? Two things like visual activity, jointly processing speech and video, figuring out where keywords are, and what the speaker, what language are they speaking, and so on. So lots of enabling technologies with varying levels of maturity. So if you have a speech signal like this, this is a spectrogram, it shows how energy is distributed across frequencies over time. You can figure out, where speech is, and then there's a technology called, for that you can imagine, right? What do you need to know? If you have, intuitively you can say, if I can measure the signal and the energy of the signal, you can figure out, oh, there's speech. Then we need to build statistical models of every person's voice is somewhat different, so we can take advantage of that, build models, of a favorite thing these days, it's neural networks. For machine learning, everything is neural networks, back to the future type of thing, deep learning. And so we can figure out who the speaker is, right? So with that, then we can figure out turn-taking dynamics, right? If you're doing measurements in two people, with mobile devices, then we can figure out what the turn-taking dynamics are. We can also figure out the context of, there's other audio, maybe that belongs to some banging sound that's happening in the environment. That's also, we can learn those patterns. And then once you have the speech, we can transcribe it using automatic speech recognition. What are they talking about, right? But there's more.
So your chest pains have been going on just for 2 days, is that right?
So the state of the art is looking for much more beyond words, right? In addition to figuring out who the speaker is, we can guess the gender from the voice. We can guess age using machine learning. So we have enough examples. We can guess what language that they're speaking. So note that I'm using the word guess. A lot of these methodologies are pattern recognition, statistical pattern recognition. So if you give enough examples of a particular type, you learn those, how those patterns are built. Then when new data comes, you evaluate the data against this pattern and see how likely it would have been generated from that kind of a model, right? And we can figure out where important words are, the dialogue act and attitude, all kinds of things people are looking for, rich information, all from one single signal. So, I just wanted to emphasize the richness of information one could get from data streams. So pattern selection and matching is at the heart of most of these technologies. So as I pointed out, right, you can ask a lot of questions. Where's vocalization? In autism, right? They're early, like infants. They're very interested in things like nonverbal vocalization, like laughter and cries and language and so on. Environment, sound type. So pattern recognition can view the three important components: training, creating these patterns. For that, you need to show enough examples of a given pattern. And then testing is like when you actually use, when you're processing your collected data from your studies against these models. And oftentimes, right, there's a mismatch between what you thought the pattern should look like and what you actually get. So you often have to move these models and their parameters to reflect the current condition. And that process is called adaptation, right? So all these are have very good statistical and mathematical underpinnings to it, and lots of algorithms are there. But that's what sort of machine learning tries to do. So I'll give you a very simple example. So say you have a piece of speech signal like this. You want to ask a question: does this speech belong to, say, the mom? Right? You're doing mobile recordings in a home environment, right? Infant-mother interactions, for example. So the training basically extracts features that characterize this pattern. Here, person, right? Usually these are spectral patterns. Each of us has a different vocal instrument. So the physics says that if you look at the spectral envelope pattern, it's going to be different. So if I capture that, that's a signature, that's a signal processing. Now with those, we have to see how generally these patterns are in this mom versus child's voice. So you build models, lots of different models. You can build simple thing. You can fit a Gaussian. It's very intuitive. You can get fancier. You can have Gaussian mixtures. You can fit hidden Markov models. Basically, put a time series on top of that, or you can train a neural network. Whatever model you fancy, you can do, and then you create mom and child. This is the training phase. Now, when new voice comes, you want to know. You're wondering, hey, does this voice belong to the mom? So you do the same feature extraction. Now you do the pattern matching. For example, you can do a likelihood calculation and see if the likelihood is greater than you set threshold. You say, well, okay, it's likely it's mom. So a lot of these things, right, pattern recognition techniques are probabilistic in a way. Template-based matchings are not very robust. Robust is a key word because of the variability in human data, human-generated data. So statistics provides a better way. You can do the same thing with speaker identification. Basically now, instead of asking, is that a person, verifying who it is, you can say, well, there are 10 possible people. Can I guess who it is? In this, that's an identification. So you build models for all these people and then figure out who has the highest likelihood for a given data, and then you can. So speech recognition gets trickier. All right, so I'm building, even with the same speech signal, we are asking all kinds of questions using signal processing and machine learning. Here, we have running stream of information, phonetic information that's flowing, right? So you have to decode. So not only do you have to recognize at every moment what sound is being created, you need to put them together and to cohere them into words and sentences and so on. And this is a fairly complex process. And people build models of sounds and models of language and use fancy algorithms to decode this, including the Viterbi algorithm, to decode. So I'll skip this part. Oh, sorry. That's to explain quantization, how to actually. So the other part I want to quickly run through. I am running out of time, I see. So we can also get paralinguistic aspects like speech prosody, intonation, rhythm, and stress.
He leaves tomorrow. He leaves tomorrow? He leaves tomorrow. He leaves tomorrow.
So you see, just by looking at intonational changes in timing, we can, we convey different kinds of information. So we can build machines to be sensitive to these kinds of things to map. We can figure out, no, just an obligatory map. Right? I'll skip that. We can also do a lot of work on emotions. It's happening after the computing. It's like, in a very exciting times these days. So by mapping things like, vocal information, language information, and, discourse information, you can actually map things to various emotional sort of representation, whether it's categorical or dimensional representations, or emotional profiles. So lots of very interesting machine learning possibilities are there. So we can also model humans as, with machine learning, right? If you think about dyadic interaction, you can imagine each human to be a stochastic system that is coupled. So my next move is going to be conditioned on what I've been doing, but also influences in the environment. But so jointly we can figure out we can predict what my next move will be. So again, Bayesian networks, dynamic Bayesian networks as a machine learning technique, we can model humans. So slowly we can build a complexity of how we do. So we can then look at system properties. Is there stability? When are they synchronizing? When are they going out of synchrony? All that stuff. What is their emotion? Same thing we can do with nonverbal things. You can model laughters and fillers with similar ideas of machine learning and the environment where things are happening. So the important point I'm saying is this like a whole bunch of sort of techniques and tools that can extract rich kind of information to enrich the sort of the study questions and the outcomes that we are after. Okay, so whole range of possibilities in state of the art. So I have a bunch of, I'm right out of time. I just want to run through a couple of sort of health examples. So for example, the marital therapy case, right? So these are the different kinds of signals we extract, right? Visually, we look at like head orientation, body orientation, velocity of arms. We can do language processing, extract words, topics they're discussing, boundaries. Just the audio alone tells us a lot, the pitch variation, spectral variation, and we can, these are the human-derived codes. They are, in this domain, people are interested in these kinds of constructs, acceptance and affect and sadness. And so what we can do is, like, we can actually automatically take these signals and predict them pretty well as human agreement, actually. But we can do more, what human coders are not able to do. We can study things like vocal entrainment, how people go in and out of synchrony, with like interesting sort of machine learning techniques. Likewise in autism, right, prosody, right, it's a very tough topic even for, in linguistics. What we found, for example, with machine learning techniques, not only are you able to do the obvious, match, derive signal features like, pitch and to map to the qualitative constructs, but we can also do things that are beyond. What we showed, for example, right, using these machine learning, by monitoring the interacting psychologists, we can predict the kind of decision that they'll come about the severity of the child that they're diagnosing. So a lot of interesting things one could do with these machine learning. We can study EDA and all that stuff. So in summary, here's my conclusion. So what I wanted to point out is that human behavior, so it's like very complex, described from varieties of perspectives. So advances in sensing, processing, and modeling support both sort of human and machine decision making. So the two things, right? One, kind of trying to map things we kind of know what to do, but maybe create more efficiency, scale up to thousands of users, for example, but also create tools for discovery. So with that, I'll stop. I have a longer thing which I'll share the slides if you're interested. Thank you very much.
Thank you so much.